After we get the two solutions, so here, y1, y2 solution, okay? y1, y2, two solutions. Yeah. Then I ask this question. Why y1, y2, these two solutions form a basis? Yeah. And we have a simple method. Yeah, remember in class we talk about there is a simple method we can use to see if y1, y2 are linearly independent. That is, y2 over y1 is a non-constant function. So that's the simple method we can use to check if y1, y2 are linearly independent. For these two functions, yes, we can use this simple way to see y1, y2 are not linearly independent. Yeah. But there is another consideration. Yeah. So last time I didn't tell you another important consideration is, although here it looks like we can use the simple method easily, to check. But think about this question. Because when we work on this concept, linearly independent concept, this y1, y2 case is only a special case. So it's not a general case. So that means this method only works for this special case, not a general case. So we can consider some more general cases. For example, if we have three functions, y1, y2, y3. This time we want to check if these three y functions are linearly independent. Then it's not easy to answer, right? Yeah, because not two, three. Three. We want to see if these three functions are linearly independent. You may ask me, yes, what do you mean linearly independent, right? For three functions. I'll give you the definition for linearly independence for two functions. But for three, you just generalize our definition for two to three. So what's that? That's k1 plus y1 times y1, k2 times y2 plus k3 y3 equals 0. If you can find the k1, k2, 3 such that the linear combination of these three functions, linear combination concept on these three functions results in a zero function. Here, this is zero function. Then we say they are linearly dependent. These three functions are linearly dependent. So for the independence, you can never find such k1, k2, k3, three constant, such that the linear combination form equals the zero function. That's the definition. All right, so based on that definition, how do you check these three functions are linearly independent? So our old simple way, this way, hard to generalize, right? Hard to generalize. How do you generalize this old simple method? You cannot. So for that reason, so we need some systematic method to help us check if these three functions are linearly independent. So from this point of view, so we can, so the last time one student, I remember Matthew mentioned that Wronskian determinant. Yeah, so we will find a determinant, the Wronskian determinant. Yeah. In part B, today, part B, we will learn that Wronskian determinant. All right, yeah. So that's the, some more explanation about the basis and the linearly independence. Now let's move to the 8.4, the last topic of part A. Yeah. Homogeneous second order linear ODE with constant coefficients. We want to solve this special type of equation. That's the simplest homogeneous second order linear ODEs. Yeah. All right. So let's look at the standard form. Yeah. Y double prime plus constant coefficient A times Y prime, and plus B constant coefficient times Y equals 0. Yeah. Let's solve this simple homogeneous second order linear ODE. Yeah. To find a solution of this one, yeah, we want to, get some insight from what we have learned before. Yeah. We have some experience we can use here. Yeah. So what experience? Yeah. Let's consider the solution for the first order. Yeah. Yeah. So this is the second order, right? Yeah. If we reduce the order by 1, we consider first order homogeneous linear equation with constant coefficient. We want to get some, some light, yeah, some information, useful information from the solution that we know before. Yeah. All right, so let's consider Y prime plus KY. So that's the simple ODE we solved before, right? Yeah. Remember when we work on the decay model, right? Decay model. So we solved this one, and we know there is a general solution, Y equals constant C times e to the negative kx. That general solution. Yeah. So from this, the form of the solution, can we get some, imagination, yeah, because our goal, we want to solve this equation. What form should the solution Y have? We want to, get this information. Yeah, because before we work on this equation, yeah, we want to, because first order, second order, at least these two types of equations should share some property, right? Share some property. Is it possible the second order, the solution also has this kind of exponential form, right? Yeah. So that's our logic reasoning. Yeah. Logic reasoning. Yeah. All right. So here, based on that understanding, yeah, so let's consider Y equals e to the lambda x. Yeah. Lambda, some constant. At this point, we do not know what's the lambda. Yeah. But just some constant to be determined later. Yeah. It is an exponential form. Yeah. E function. Yeah. We want to try if our solution, if it's possible to get a solution with this E function form. Okay, yeah? Otherwise, if you do not have the information from the first order, how do you guess this form, right? Why you do not guess sine, cosine, okay? Why you do not guess natural log? Why you do not guess some polynomial, right? Yeah, so, but because we have some information from the first order solution. So when we make our guess, yeah, so we naturally we connect to the first order solution. Yeah. All right. So now, so let's plug in this E function into our original second order ODE. Yeah. So y prime, y double prime. Yeah. Then after simplification, we get this form. Yeah. We know the E function is non-zero. Yeah. So if the left-hand side equals 0, that means this coefficient part must be 0. Okay? The coefficient part must be 0. So we get a new equation. Yeah. This new equation is an algebraic equation, not differential equation. Okay? Yeah. So here you can see we convert original differential equation to an algebraic equation. Yeah. So that equation we call it characteristic equation. Yeah. Yeah. Gamma lambda squared plus a lambda plus b, ab given, so we can apply the quadratic formula to find y1, find lambda, lambda 1, lambda 2. Yeah. We also call this function equation auxiliary equation. Yeah. But most people call characteristic equation. Yeah. Then, by the quadratic formula, lambda 1, lambda 2. Yeah. So these two lambda constants can be determined. Yeah. Determined. All right. Yeah. So it looks like we can write out the two solutions immediately. Right? Yeah. All right. But when we apply the quadratic formula, the expression under the square root, yeah, because there are a few cases, yeah, the expression under the square root could be positive, negative, and 0. There are 3 cases. Yeah. So here we consider these 3 cases. The first case, a squared minus 4b is positive. So we have 2 distinct real roots. All right, yeah. But the second case, when a squared minus 4b equals 0, we have 1 real double root. Yeah, 1, 0, but 1 real root, but it's a double root. It's not a single root. Okay? Yeah? Yeah. Some of you probably want to ask, what's the meaning of double root, right? Yeah. So if some students do not understand the meaning of double root means y minus y0. Y0 is 0, but double root square equals 0. Okay? Yeah. Single root means y minus single. Okay? Yeah. No square equals 0. Yeah. Single root. Double root. Yeah. Here, it's a double root. It's slightly different. Yeah. Some people may argue, what's the difference? Because single root, double root, we cannot see the difference because there is only one possibility why lambda 0 is the root. Yeah. Actually, there is a possibility. Okay? That square, if there is a square or not, there is a possibility. Yes. Yeah. there is a possibility. Okay? Yeah. 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 Sometimes you cannot see what's the difference, but sometimes you can see. Okay? Yeah. For example, one property. If we take a derivative on the left-hand side, the derivative of left-hand side, when you have a double root, you still have a single root, right? Its derivative still has that lambda 0 single root. But the derivative of the single root, then you don't have that single root. So that's difference. So that's one important difference. Yeah. So that's why when we say double root, single root, there are some important difference between these two cases. Yeah. All right. Case number 3, two complex roots when a squared minus 4b equals 0, less than 0. Yeah. So these 3 cases. Yeah. All right. Because for case number 3, lambda 1, lambda 2, they are complex numbers. If you use e to the lambda 1x, e to the lambda 2x as your solution, you will get 2 complex solutions. Okay? Yeah. Although many people, when they see complex functions, they feel very comfortable. Yeah. But sometimes some people still they do not feel comfortable working on complex functions, right? Yeah. All right. Yeah. So now let's look at the last slide. I want to write the specific forms of these 3 cases explicitly. Yeah. So that you can get a better understanding. Yeah. All right. Now we need to work on these 3 cases one by one. Yeah. The first case, that's easy, right? Lambda to 2 real numbers. Yeah. Second one, yeah, these 3 cases. So the first case, y1 equals e to the lambda 1 x, y2 equals e to the lambda 2x. That's all you need. Yeah. Right? Yeah. Lambda 1, lambda 2 real numbers, that's all you need. Yeah. Now let's move to case number 2. Case number 2, this time y1, y2 are the same number, lambda, yeah, if we use a lambda, equals negative a over 2. Yeah. So you can write the first function, y1 equals e to the negative ax over 2. But what's the second function? What's the y2? So you can write out y1 explicitly, but how do you write the second function, y2? Right? Yeah. How do you write the second function, y2? Yeah. Because from the formula we have so far, we do not have any information to write the second solution. Some people may feel this second order linear homogeneous ODE may not have the second. Only one solution. It's not, because we know second order ODE homogeneous, it should always have 2 solutions. Yeah. If you only get 1, that means you need to find the second one. Okay? You still need to find the second one. Yeah. Yeah. Here, I'll give you the second one. y2 equals x times e to the x times the first solution. Yeah. Can you see why y2 is the solution? X times, yeah, y1, yeah. All right. actually we can find y2. If y1 is known, do you know how to find y2? If y1 is known, do we have a method to find y2 from known y1? Remember? We have formula, right? If y1 is given, we can apply some formula to help us find y2. Yeah. So you can use that method. Yeah. Here, to save some time, I do not do that derivation. Yeah. Yeah. Okay. Yeah. Just let you know. You can find it by yourselves. Yeah. All right. Let's move to case number 3. Case number 3. This time we need to use imaginary I in our formula, lambda 1, lambda 2, yeah, in our discussion. Yeah. Yeah. And we know the square root part is a positive number. Yeah. And to make the expression as simple as possible, we introduce a variable omega to represent that square root. Okay? Yeah. So then we can write y1, y2 in this way. But here you can see when I write y1, y2 in this way, I use sine, cosine, and the imaginary part is gone. You do not see I. You do not see the imaginary part. And these two functions are real functions. Yeah. Because when we use these two real functions as our solutions, it's more friendly, right? In our real world applications. Yeah. They are normal functions. Yeah. We want to avoid complex functions in our real world applications, if we can. Okay? Yeah. So here we avoid the complex solutions or we say this way, we replace the original complex solutions by two other solutions, but they are equivalent. Okay? Yeah. 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 All right. But here, I want to explain why we can do it in this way. All right? Yeah, let me explain why we get around that complex representations. Yeah. So let's recall the Euler formula. E to the I omega equals cosine omega plus I times sine omega. That's the famous Euler formula. Yeah. Okay. Yeah. Here we use this formula. All right. Because this one there is I there. Okay. Yeah. So the first time when we write our complex form, yeah, we keep that I. Okay. We keep that I. Yeah. All right. Here I use y1 star to represent C, constant C times I omega x, yeah. And y star 2 equals C times negative I, yeah. So here you can see, yeah. So here I consider this, yeah. Yeah. But connect to y1x, right? So that these two are supposed to be the two solutions. Yeah. But this one, yeah, remember, equals e to the negative ax over 2 times e to the I omega x, right? Yeah. This one equals e to the negative ax over 2 times e to the negative I omega x. Yeah. But this part, these two solutions, this part the same. Okay, same. For simplicity, we do not need to copy that same function. Okay, we just look at the, the critical part. Yeah. So that's why here we do not consider that, the same function part. Yeah. So here we use a constant c to, before that e to the I omega function. Yeah. All right. Then we apply the Euler formula. Okay. Yeah. Yeah. Plus minus the difference. These two, the difference is plus minus. All right. Then remember, we can do linear combination, right? Yes. Because we know for the homogeneous, second order, homogeneous linear ODE, if there are two different solutions there, then when we apply any linear combination on these two solutions, we will get a new solution. Yeah, so that's what we learned last time. Now let's do linear combination. The first linear combination, let's just add up these two solutions. Y1 star plus Y2 star. Okay, then you have cancellation, right? The second term, yeah, plus minus IC sine omega x. That term can be canceled out. Yeah. So the first term should be double, right? 2c omega x. Yeah. But double and 2c, yeah, because c is an arbitrary constant, right? 2c is also arbitrary constant, right? So why you need to keep that too, right? Because c already arbitrary constant. Yeah. So here, yeah. So I want to simplify the representation. Yeah. Although the answer should be 2c cosine, yeah, but we can put that 2 inside the c, right? Can we? Yeah, because c is an arbitrary constant. Yeah. So that's why we don't need to keep that 2. Yeah. So that's why here we still use c. It's not typo. Yeah. Yeah, because the c can be any non-zero constant. Non-zero constant. So we cover all the possible constant, right? So we do not miss any non-zero constant. Yeah. All right. Similarly, for the I, so we keep that c, but that I, so although this I is an imaginary number, but it is a constant, right? Is I a constant? I is also a constant, okay? So I is a constant, yeah. But if I is constant, I is a non-zero constant, right? I is a non-zero constant. Yeah. Okay, yeah? So, the constant multiple of a function, yeah, because, so here, we consider sine omega x. Yeah. There is a constant multiple, okay? C star, constant multiple, all right? Yeah. For the constant multiple, yeah, all right. But with that I, the constant becomes an imaginary number. Yeah. And here we want to avoid imaginary related terms. Yeah. Yeah. So here we just cross out I, because I is a non-zero constant. If we cross out a non-zero constant, we do not change the representation, right? Yeah, it's a non-zero constant. So we do not include it. Yeah. So here, yeah. Because when we select a representative, yeah, because our Y2, we just select a representative. Yeah. Okay. When we select representative, we just use a non-zero constant, and we do not need to include the I. Okay. Yeah. Because in real-world applications, most of the time, yeah, so it's not all the time, most of the time, yeah. So we want to use real functions as representative, okay? Not imaginary function, not a complex function as the representative. Yeah. So that's why our second one, we use the real function representative. Okay? Yeah. So we have freedom to choose. Okay? So we have freedom to choose the representative. Yeah. So for that reason, now finally, you get y1, y2 functions without any I-related terms. Yeah. They are both real functions. Yeah. All right. Yeah. So that's the complete solution for this simple, our simplest second order linear homogeneous ODE. Yeah. So we completed. Yeah. All right. Yeah. Next, let me. Yeah. So any question? So I need to move to part B. Yeah. Any question? Let me know. I can answer a few questions. Then move to part B. Yeah. Yeah. So let me drink some water so you think about if you have any question. All right, let's move to part B. Part B. All right. Part B. So we have a, big important task to do. That is existence and the uniqueness of solutions. Yeah. So this topic is very abstract. Okay. So it's not about calculation. Yeah. So it's a theoretical understanding. Yeah. So could be a little hard for you. Yeah. All right. Before we do that topic, yeah, that's our main topic in this part. Before we do that, let us solve another special type of second order homogeneous linear ODE. Yeah. Another interesting type. So it's called the SP.1 topic, Euler-Cauchy equation. Yeah. All right. The form, the basic form, x squared times y double prime plus ax y prime plus b. Yeah. So you can see the new part, x squared, there is an x, yeah, different from our previous simple form. Yeah. Here, it looks a little harder. Yeah. Yeah. But this equation has some special form. Yeah. This form is so special, so we can take advantage of the special structure of this equation so that we can, still we can find a simple, easy way to find the solution. Yeah. All right, so here. We consider y equals a to the mth power. This special form. Yeah. This time it's not an e function, right? Yeah. Yeah. The previous one we used the e function, but this time we use the monomial function. Yeah. X to the m. So what's that? The m is some constant to be determined. Yeah. Some constant to be determined. Yeah. Yeah. But you may ask me, some students may ask, how do you know you can choose this form, right? Yeah. You can choose this form. Yeah. Yeah. All right. Yeah. Yeah. So the understanding could be like this. Yeah. Understanding could be like this. Yeah. Because here, when when y is a monomial, so here, actually, here we should not call it monomial, all right? Yeah. So this function we should not call monomial. We should call power function. Power function. Not a monomial. Do you know the difference? Yeah. Because when we say monomial, then that m must be integer, right? That m must be non-negative integer. That's the monomial, okay? M must be non-negative integer. Then we can call it monomial. Yeah. But our m here could be non-integer, could be negative numbers, could be non-integer. Yeah. So that's why, the right name for it, it's a power function, not a monomial. Okay, yeah? All right. Then we take derivative and a second derivative. Yeah. The first derivative by the power rule. Yeah. Derivative, we have a power rule. So we apply the power rule, we get this m times x to the m minus 1. So you can see the exponent number is reduced by 1. Yeah, reduced by 1. Yeah, but reduced by 1, we have an extra x here. So this extra x compensates that one lower number. Yeah, because that you have that extra x, you multiply it, then you recover the exponent from m minus 1 to m again. That's for the middle term. The first term, y double prime, we apply the power rule twice. So the exponent becomes m minus 2, but you have this x squared, you can use that square to help you recover the exponent number to m again. Then, for all the three terms, when you look at the power function, the exponent part, they have the same exponent number. That's the reason we take advantage of the special structure. Yeah. So why we use the power function? Yeah. Because when we use the power function, so we can do factorization. That power function is factorized. Yeah. Then its coefficient should be 0. Then we have a, characteristic function, right? Yeah. Similar to our previous example, this time we have a characteristic function or auxiliary, characteristic equation or auxiliary equation. Yeah. After simplification, so we get, this quadratic equation for variable m. Yeah. And we can still apply the quadratic formula, m1, m2. Okay, yeah, m1, m2. Yeah. 3 cases, right? Yeah, similar to our discussion. Yeah, the 3 cases. Yeah. The first case, we can write the real solutions immediately. Yeah. But the second case, it's a real double root. Yeah, double root. Yeah. Yeah. We can write the first solution immediately, but how about the second solution? Second solution, you need to use the method we learned before. Yeah. We can calculate the second solution. Yeah. But here the result. The first solution multiply natural log of x. That's the second solution. Yeah. Yeah. Okay. So y, we apply the same method. Yeah. First, if the first solution is given, we apply that reduction of the order, right? Yeah, reduction of the order, that method, we can find the second solution. Yeah, all right. Then, for the complex case, yeah, omega, we need to use that omega number, okay? Yeah, so we define this omega number. Yeah. So then sine, cosine, okay? Yeah, so two solutions. Yeah. To the m, yeah, you know, we have that m, okay? Yeah, yeah. But, you know, this is original complex, but we want to convert it to two equivalent real functions. Yeah, the first real function, the second real function. Yeah, equivalent. Yeah. When we choose our basis, we have a lot of freedom. Yeah. So here, when we choose our two basis functions, we want to avoid the complex functions. So in our large pool, remember, all the general solutions, we put it in a large pool, and inside this pool, we choose two real functions as the representative for all the general solutions. Yeah. So here, yeah, so we apply the Euler formula. Yeah, so we choose these two real functions. You know, yeah, to avoid the complex function solution. All right, yeah, so we complete this another simple second order linear homogeneous ODE. Yeah. All right. Next, B.2. Yeah. Now we need to study this topic, yeah, theoretical topic, existence and the uniqueness of solutions. Yeah. Two subtopics. Oh, yeah. What question?
So, with the general form,
Uh-huh.
or the Cauchy-Euler equation with
Yeah.
imaginary terms,
Right.
the natural log, would we need an absolute value for
Natural log what?
available?
Yeah. So this part in omega times natural log.
For the bottom.
The bottom, yeah, yeah, because we apply Euler formula, right? Yeah, we apply for Euler formula, e to the I omega, this one, yeah. The whole thing we should put in the cosine x, right? Omega natural log x. That, then I, right? Natural log inside, okay?
Yeah, would we need the absolute value?
Need what value? Oh, absolute. Oh, I understand. Yeah, you want to put absolute value. Yeah, think about. Yeah, this point. Yeah, yeah, absolute. Okay, yeah. Oh, yeah. You're right. Yeah. So actually, yeah. So we need to go back to the. Right, yeah, because this place should be absolute value, right? Yeah, so things like, because this place comes from the integral, yeah. So then this natural log, when we calculate that, so here, e to the, oh, just a minute. Right. Just a minute. Right. Yeah, natural log. Yeah, let me see. How do we get this omega natural log? Yeah, so this omega, yeah, e. All right. Yeah, oh, okay. Yeah. So x to the, oh, yeah. Yeah, actually, yeah.
I remember reading that the Cauchy-Euler equation exists over two intervals, negative infinity to 0.
Right. If you do integral, you will have absolute value. Yeah. If you do integral, you have absolute value. Yeah. Yeah. So xm1, xm2. xm1, this m, that m2 omega. Yeah. Yeah. Actually, yeah. All right. Yeah. So yeah, this part. Yeah. There is some explanation here. Yeah. Good. Yeah. All right. Yeah. And actually, this part also there is an absolute value question. Yeah. 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 Good point. Yeah. All right. Yeah. Because here we do not know x positive, negative. So we allow x to be negative. Yeah. So when we take integral, we need to make sure, absolute value. Yeah. Yeah. Right. Yeah. Yeah. So. Yeah. All right. Yeah. Okay. Yeah. So let me try to make it this rigorous. Yeah. Make this rigorous. Yeah. All right. Yeah. So I will double check. Try to make the whole story rigorous. Yeah. All right. Yeah. So next time I will explain. Yeah. I will improve the explanation. Yeah. All right. Good. Yeah. So before the break time. Yeah. So let us see how much we can go. Okay. Yeah. First, B.2, first order linear ODE existence theorem. Yeah. But remember this part, this module, we talk about the second order, not the first order. The reason I put the first order here is the first order topic should be in our, chapter 1, and it should be in module 1, but I didn't talk about, in module 1, I didn't talk about this topic. Yeah. So the reason I want to save some time, yeah, because if I talk about this topic in the first module, then in the second module, I also need to talk about this topic for the second order, right? So then I just combine, this topic for first order, second order together. So in that way, I can save some time. Okay? Yeah, because I do not explain the same thing twice. Yeah. Yeah. So that's the reason I put this first order topic in our module 2. Well, all right. Let's look at the first order case, linear ODE, the existence problem. Yeah. Consider the initial value problem for the first order. Yeah. All right. Simple example for existence. Yeah. So because at this point, when we are given a first order ODE, usually we assume there is some solution. So we want to find it. Yeah. We just need to find that solution. But we never consider the case the solution may not exist, right? Yeah, there is a possibility the solution does not exist. Yeah. So here we need to consider that possibility. Yeah. So let's look at the first simple example. Yeah. This example is a trivial example. Yeah. Trivial example. So you can see, based on the equation given, we can see there is no solution. So why? Because left-hand side, sum of two absolute values equals 0. That means each one should be 0, right? The first term, second term, each one should be 0. If the second term should be 0, then y should be 0 everywhere, right? But how can you make y of 0 equals 1? It's impossible. Yeah. So, yeah. Oh, right. So, yeah. So you never have this y of 0 equals 1. Then it's a contradiction. That means there is no solution. Yeah. So this is a trivial example. Yeah. So we do not need, we can see it immediately. Yeah. 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 Although it's not a linear ODE, but from this equation we want to see sometimes the first order ODE initial value problem may not have any solution. Yeah. Let's look at another example. Yeah, let me look at the time I have. Another example. Yeah. All right. So for this example, let us discuss it after the break. Let's take a 10-minute break. Yeah. So then we discuss this. This is a non-trivial example. Yeah. Look at this non-trivial example. All right. Yeah. Take a break. Yeah.